High resolution and high refresh rate displays push GPUs to the limit. When the GPU bandwidth or power budget is limited, we need to choose between low resolution and low refresh rate. We propose a visual model that can best find the compromise between the two. Given a physical specification of a display and the content of the screen, we can find the optimum frame rate and shading rate for each 16 by 16 VRS block. We can maximize the visual quality of real-time rendering without eye tracking and at a minimum computational overhead. Future rendering will be adaptive and will make the best use of high resolution and high refresh rate displays.
Displacement mapping is a powerful tool for adding geometric details over a surface mesh using a texture, but ray tracing displaced surfaces is challenging as microdetails must be made random accessible. Tessellation requires discretizing texture-mapped displaced surfaces, leading to unacceptable memory usage for high-resolution displacement maps. We propose instead a displacement-centric acceleration structure that can be mapped as a texture on triangle meshes. The actual bounding volumes are only computed on the fly at ray query time. Our method enables interactive design choices, such as modifying the displacement amplitude or increasing the amount of tiling, in real time with minimal memory overhead. We also support geomorph level of details and a range of local reconstruction filters.
We present a novel approach to the sky materials and function integral. We present a novel approach to the sky materials and features, as well as statistical perturbations. This model is also powerful. The diffraction integral decouples under this model, and we are able to efficiently render full wave effects. Our theory goes beyond the state of the art by accounting for partial coherence and serves to unify several wave optics rendering formalisms into one.
We propose a method that decomposes a single flash image into spatial fields of BRDF components that, when rendered, resemble the input image. Our method is fully self-supervised and is trained on real flash images. We first encode a flash image to a latent space Z. In combination with noise, Z serves as a condition for our synthesis unit architecture that reshapes noise crops to BRDF channels. Finally, we render the generated maps in a differentiable manner. We can get diverse outputs of the same image by reseeding the noise. We can also sample the output maps infinitely. Please listen to our talk for more details.
Predictive transfer theory is used to model how light interacts with participating media. Recently, this theory has been generalized to handle materials with organized macrostructures. To derive the backscattering parameters used by the RTT, existing methods rely on far-field approximation and independent scattering, neglecting important near-field interaction between particles, including interparticle diffraction. We relax this assumption by introducing a particle cluster-based technique to systematically compute the scattering parameters of medium composed by clusters of particles. With our method, we can simulate, for example, multispectral effects for anisotropic and spatially correlated scatters distributions. For more details, please come to our talk.
Rendering simulates light transport as a 2D image, which is a function of scene parameter theta. Differential rendering allows us to compute derivatives of the image with respect to scene parameters. The difference of images with an infinitesimal motion converges to the derivative image. Transient rendering simulates time-resolved light propagation, where light source and the camera function depend on time. In this work, we propose the differentiable transient rendering method to compute the derivatives of transient images. We also introduce interesting applications such as optimizing transparent objects and advanced non-line of sight imaging.
In this work, we present a new theory of differentiable time-gated rendering. It offers the generality to handle global illumination and differentiate with arbitrary scene parameters. We introduce a new path length boundary integral. This deals with jump discontinuities in time gate functions and can be computed efficiently using our Monte Carlo estimators. Our technique allows solving inverse time-gated rendering problems with full interreflection using a non-line of sight configuration. Please come to our talk for more details.
So that's it for this year's Technical Papers Fast Forward. Please join us in the closing session on Friday, where Jiggy Lee, the SIGGRAPH Asia 2022 Technical Papers Chair, will give an introduction to the SIGGRAPH Asia 2022 Technical Papers Program.